Good afternoon. In class diagram techniques, we model things in our problem as objects. And for each type of things, we define a class to specify them. And for each type of interaction, we define an association to specify in the class diagram. So we have already studied how to specify a classes, how to specify associations. In class diagram techniques, altogether there are three types of relationship: association, aggregation, and generalization. So we have already studied associations. So today I'm going to proceed to talk about aggregation, and after that will be generalization. Among all the interactions, there is one special kind of interaction that is type part and assembly kind of interaction. So in class diagram techniques, these special types of part and assembly kind of interactions, we use a special relationship type aggregation to differentiate them from others kind of associations. So in other words, aggregation is not a new concept. Aggregation is a special types of association. Okay. And these special types of association is to specify part and assembly kind of interactions. Okay, this is an example here. Paragraph is part of documents. Okay, when you prepare documents, you have many paragraphs. A document usually is formed by a collection of paragraphs. So paragraph is part of one document. Okay? And each document have many paragraphs, can have many paragraphs in it. Okay? So this is a special types of interaction, is a part and assembly kind of interactions. Okay? Documents is assembly of many paragraphs together. Okay? And paragraph is part of documents. So we use aggregation to specify it. This is the notation to define aggregations. So since aggregation is a special types of association, you can see that the notation is also similar to associations. Okay? So the only difference is we have a small diamond. Instead of putting a diamond in the center, similar to what we do in some associations, we put the diamonds, we attach a diamond to the class representing the assembly. So in this case, in this particular aggregation, document is served as assembly. Document is assembly of many paragraphs together. So we attach a small diamond to the documents, and we connect a line to the part, to the class representing parts. So show that paragraphs are part of documents. So when you look at the, when you see such notation, you will know that this is aggregations. Okay, have a diamond attached to one class, that is the aggregation, and the class that attached with the diamond play the role of assembly in the aggregations. Okay, and since aggregation is a special types of association, okay, we can also define multiplicity in aggregations. The meaning, the definition of multiplicity is exactly the same with general associations. Okay, so we have a 1 here, we have a multiplicity exactly 1 here. It means that, okay, when you interpret the multiplicity, always reference to other classes. So over here, there's only one other class. So it means, this means each paragraph, each instance of this class, that means each paragraph is part of exactly one document. And here the multiplicity, 0 to many, it means that each document has 0 to many paragraphs. Okay. Some may have many paragraphs, some may not have any paragraph there yet because we have just set up the document format only. We have not written anything yet. Okay, and below there's another aggregation. You can see from here, here is to define sentence is part of paragraph. Okay. So each sentence is part of exactly one paragraph. That means paragraphs do not share sentences. And every paragraph have 0 to many sentences. Okay? So this is another aggregation. Okay. Okay, since sentence is part of paragraph and paragraph is part of documents. Okay. So that also implies that sentence is also part of document. So in aggregation, you have this transitivity property. Okay. So these special types of association, aggregation, have transitivity property. Okay. Once if A is part of B and B is part of C, automatically A is also a part of C. This is the property of transitivity. Right? Okay, this is so much about aggregations. Okay, now we proceed to the last type, last relationship type. That is generalizations. Generalization, the purpose of generalization is for us to represent type and subtype. Okay? To show that a general type has many subtypes, okay? To represent a type and subtype kind of relationship. Okay? So that means the objective of using generalization is to define, to specify a classification in our class diagram. Okay? If you classify a type of things into a number of subtypes, then we will define generalization to show it. In this case, the type, the general type, is represented by a superclass, by a class called the superclass. And each subtype, okay, so when we use a generalization, we classify a type into subtype. The general type is represented by the superclass in the generalization. There's only one superclass in any generalization. And each subtype will be represented by a subclass in the generalization. So a generalization can only have one superclass and may have many subclasses. Depends on how many subtypes you have. Like this case, okay, here show that, okay, this is to represent the general type. So I define a class called a superclass to represent the general type X. And we have two subtypes, Y and Z. You can see from here that, so each subclass is to represent a subtype. And this is the notation for you to define generalization. Okay? So we draw an arrow to point from each subclass to the superclass. We draw a hollow arrow. We draw an arrow with hollow arrowhead, point from each subclass to the superclass. If you see such notation, means this is a generalization. And under this generalization, we classify the superclass X into two subclasses, Y and Z. So since this is a type and subtype kind of representations, so each Each instance, that means of y, that means each object of y is definitely an instance of x. So that means an object of x. Okay, and each instant object is also an instant of x. So that means in the generalization, an instant of any of the subclasses is definitely an instant of the superclass, because any things that belong to the subtype definitely also belong to the supertype, general type. And when you define generalizations, when you define a generalization as such, then every subclass, okay, by default, every subclass will inherit all the properties from the superclass. Okay, here property, when we say a property of a class, what does it mean? Okay, property of a class means attributes and operation, because every class, inside a class you can define attribute and operation. So when you say properties of a class means attribute, class attribute, and operation defined in the class. So that means by default, every subclass will inherit all the attribute and operation from the superclass. Okay, so that means if you just define a subclass, okay, without defining anything here, okay, without defining any attribute and operation, just define, just give the subclass a name. That's all. Just give the subclass a name. Assuming that we take out this one, then this subclass Y will have all the attribute and operation of the superclass. Okay, so that is what inheritance means. So this is first point. Second point is that if the attribute or operation from the superclass is not suitable for the subclass, okay, if we have a subclass, the attribute, any of the attribute or operation from there not suitable for the subclass, then we can overwrite it. Okay. The way to overwrite it is by redefinition, redefine it. That means, like this case, okay, here you can see the superclass, I have an attribute x2, right? In the subclass, I write x2 here again. That means I redefined it. Okay, by doing so, the attribute x2 from the superclass x will not be inherited down over here, because this subclass y redefined it. Okay, so subclass y will have its own attribute x2. Okay, the one from superclass will not be inherited down. So this is the way to override those unwanted attribute from the or operation from the superclass. Okay. Second point. The third point, in addition to overriding any unwanted attribute from the superclass, okay, a subclass can also define new attribute, define totally new attribute, okay, to represent new properties specific to the subclass. Okay. Like this case, y2. Okay, y2 here I will define in subclass y, and this y2 is, there is no y2 from the superclass, you can see from here. So that means y2 is a new attribute defined in the subclass y itself. Okay, so you can, okay, by default, if you don't do anything in the subclass we have all the attribute and operation from the superclass. Okay, that's by default. Okay, but in the subclass you can override those unwanted attribute by redefinition. I have already shown you. And in the subclass you can add in new attribute that to describe specific property to the subclass. So you have all these mechanism, okay, to define in your subclass. Okay. So over here, by the point I have just discussed, so straight away you can see that over here the subclass Y have how many attributes altogether? Okay. From inheritance and from overriding, from defining new one. So altogether, subclass Y have how many attributes altogether? Subclass Y have how many attributes altogether? Have three attributes altogether. By defining in this way, subclass Y have 3 attributes altogether. X1 inherited from superclass X. X1, because subclass Y does not do anything to X1, does not redefine it. So by default, you will inherit down. Subclass Y have attribute X1, and in addition, subclass Y also have attribute X2. Okay, X2 is not from the superclass, it's defined in the subclass Y itself. And subclass Y also have a new attribute Y2, okay, that is defined in the subclass. So altogether, in this class diagram, okay, subclass Y we have 3 attributes. X1 from X and X2, Y2 defined in the subclass itself. Okay, how about Z? Here, Z, we have 3 attributes also, okay? So for the case of Z, the subclass Z, you can see that there's no redefinition of X1 and X2. So by default, both X1 and X2 from the superclass X will be inherited down to subclass Z. That means subclass Z, we have 2 attributes, X1 and X2 from X. Okay, and have a new attribute Z1 defined in the subclass Z itself. Okay, that is how it works when you define a generalization, how the properties, that is how subclass will have the properties from the superclass. Okay, and in addition, like what we have discussed, any instance of Y will definitely be an instance of X because Y is a subclass of X. Any instance of Z will also be an instance of X. Okay, now we have a more concrete example to show you how to use generalizations. Okay, before you see this more concrete example, there's one point I'd like to highlight to you. For generalization as well as for aggregation, you have 2 alternative notation. The one we have seen earlier, this is the first alternative. You can draw arrow with hollow arrowhead point from each subclass to the superclass individually, like this case. Okay. You can also show a general. If you have multiple subclasses, you can also join all the subclasses together as such. Join them together. Okay, draw 9 to join them together. Then after that, just use one arrowhead. Just use one arrow to point to the superclass. Okay, that is the second alternative for you to draw a generalization in a class diagram. So we have 2 alternative notation. Later you will see that for aggregation we also have 2 alternative notation. I will show you later. Okay, so over here, what do we define? Okay, over here, this part of the class diagram show that in a company, employee is classified into 2 types. Hourly employee and salary employee. That means those paid by hour and those paid by months. Okay, so the employee in this company is classified into 2 types. Okay, so the general employee, that means every employee is represented by this class, superclass, okay, and each employee from each subtypes, okay, is represented separately by each subclass. So each hourly employee is specified by this class. Each salary employee is specified by the second subclass. Okay, so this is as I told you earlier, the objective of generalization is to define classification in our class diagram. So over here, we use generalization to show the classification of employees in the company into two types, hourly employee and salary employee. And follow the rule, follow the property we have just discussed. You can see that for hourly employee, we have how many attributes? When we draw a rectangle, divide into three regions. Okay, the first region we always show the name of a class, and the second region we always show the attribute. The third region we always show operations. Bear this in mind. Okay, and so from this generalization, we can see that hourly employee have how many attributes? 4 attributes altogether. Okay, 2 from general employee class, employee number, employee name, and 2 defined in hourly employee class itself, hour rate and overtime rate. So altogether have 4 attributes. Okay. So both attributes from the superclass will be inherited down by default because this subclass does not redefine it again. Okay. How about operation? We have how many operations? Hourly employee have how many operations? Okay. Salary here means computation of salary. Since we put the name salary under operation, it means the computation is a task. It's a computation of salary. So over here, hourly employee has how many operations altogether in this general? 2 also. 2 only. Registered new from employee from the superclass, and salary defined in this subclass itself. Okay, so since in this subclass we redefine salary, this particular operation, so the salary from the general employee class will not be inherited down. So altogether, hourly employee will have 2 operations. Salary employee, in this case, we have 3 attributes because 1 attribute defined in this subclass itself and 2 attributes from the superclass. And again, we have 2 operations. So, and from this diagram, you can see that certainly every hourly employee is an employee. Okay, every hourly employee in the company is also an employee in the company. So it's very clear-cut. Okay. So since hourly employee is a subtype of general employee, so every hourly employee, okay, every instance of this class is also an instance of this class. That is what we have. That's what I have highlighted earlier. Every instance of a subclass is definitely an instance of the superclass. Okay, on the left-hand side, we have another generalization. We have another separate generalization. Over here, we show that class Y is a subclass of X. Okay, that means Y is a subclass of X, and X is the superclass in this generalization. So you can see that in this generalization, we only have 1 subclass. So it does not mean that in the generalization you have to define multiple subclasses. You may have a case that you only need to define 1 subclass. That is possible. Okay, so same principle. You can tell how many attributes and how many operation class Y have. Follow the same principle what we have discussed just now. Okay, so I will leave this one to you. I will not go through it again. Okay, now we come to another point with regard to generalizations. Okay, as we mentioned earlier, each instance, that means each object of a subclass is definitely an instance of the superclass. Okay, so we have we use this one as an example to illustrate another point I'm going to mention to you soon. Okay, over here we have a generalization to show a classification of NTU student. Okay, we classified the general NTU student, okay, single out two types, okay, two subtypes, EE student and School of Computer Engineering student. So we have two subclasses here. So it's very clear that each EE student is also an NTU student. Okay. So this is the basic principle of a generalization. Okay. But the other way around may not true. An NTU student may not be an instance of, may not be a student of EE, may not be a student from SCE as well. So that means, in other words, in general, although each instance of a subclass is definitely an instance of the superclass, but the other way around, that means an instance of the superclass may not be an instance of any of the subclasses. Okay. So this is another important point. The other way around, you follow the arrow, it's always true. Each instance of a subclass is definitely an instance of the superclass, but if you try to move the other way around, may not be true in general. An NTU student may not be a EE student, may not be a SCE student. It could be an NBS School of Business student also. Okay? So this is another point, another basic property of generalization I like to emphasize to you. Okay. It is only when you have a generalization to represent a complete exhaustive classifications, then an instance of the superclass will be an instance of one of the subclass. Okay? But when you do classification, you may not do a complete one. Okay? You may do a partial classification. Like this case, you classify NTU student, single out only two types because you want to focus on these two schools only. Okay, so we have discussed most of the concept in the class diagram techniques. This slide give you some example, okay, to summarize the understanding of this concept. Okay, so association, firstly, the relationship type. Okay. We have three types of relationship that we can define in the class diagram techniques. The first one is association. So the purpose of association is to represent a type of interaction. Okay. So here we have some example listed down. I will leave it to you to go through. Okay. So association is to represent a type of interactions. Okay. Instant association. Okay. Instant association, okay, is to represent an individual interaction, an individual specific piece of interactions. And aggregations is to represent a type of part and assembly kind of interaction. A type of part and assembly kind of interaction is also type. Okay. And each individual part and assembly interactions will be an instance of aggregations. And generalization is totally different from aggregation and association. Generalization does not show interaction between different objects. Okay. Generalization is to define classification. In a generalization, we do not refer to different objects. So a EE student is an NTU student. So we refer to only one single object, the EE student. Okay. So does not involve different objects. Always refer to a single object in the generalizations. So these are their basic property. Okay. This slide summarize their differences. Okay. Firstly, between aggregation and association. Okay. aggregation is a special types of association, as I mentioned to you earlier. Okay, and that is the part and assembly kind of interaction. Both are interactions, but aggregation is to show a more tidy couple. That is part and assembly kind of interactions. But associations is to show general interactions. Okay, how about association and generalization? Okay, generalization is very much different from association and aggregation. Okay, in generalization, okay, we do not refer to different objects. Okay, when we look at a generalization, we always refer to single object, as I mentioned to you earlier. We do not refer to different object. A AAA student is an NTU student. Okay. No different object involved. But when we refer to association or aggregation, we always refer to different object. Lecturer, kid, student. Okay. I'm one lecturer here. Okay. I teach you. Okay. So there are two objects involved, myself and yourself. Okay? So different objects always refer to different objects. And aggregations also refer to different objects. Okay? A tire is part of a car. Tire is object and a car is also object. These two are different objects. Okay? So refer to different objects. That make generalization very much different from association and aggregation, and that is the main difference. Okay, in addition to that, aggregation is to show part and assembly kind of interaction. Okay, but generalization is to show type and subtype. It's a kind of, that means a subtype is a kind of the general type. Okay. So that is a different concept to represent totally different concept. Okay, this slide. In this slide, there's only one point I would like to highlight to you. Okay, just now I mentioned to you that for generalization, we have two alternative notation. Okay, one is to draw arrow to point from a subclass to the superclass individually. Okay. Another one, the second alternative to show generalization is by joining them together, okay, joining all the subclasses together and just draw one arrow to point to the superclass. Okay? So similarly, aggregation also have two alternative notation. We can draw 9 with diamond attached to the assembly class individually. For this case, over here, in these aggregations, okay, tire is part of car is assembly. And car engine is also part of car. Okay? So we have two parts class in this aggregation. So one way to show them is to draw separate 9 with diamond attached to the assembly class. Okay? And we can join them together also. As such, we can join the part classes together and just connect to all two of them together with a small diamond attached to the assembly class. Okay. So it's quite similar to the case of generalizations. Okay, so we have only a few more slides to go through in terms of class diagram techniques. Okay. Over here, firstly, we summarize the property of each relationship type. Okay. Generalization, aggregation, and association. Okay. So we have all these property we have already discussed earlier. I will not go through them again. Okay. What I want to highlight to you is the last part. Okay. How to determine whether a relationship type is a generalization or is it aggregation or is it association? Okay. So if you have a relationship type, to determine whether when we draw a class diagram, if we have a relationship type among classes, okay, and we want to now we are not too sure yet. We have to decide whether it is a aggregation or is it association or is it generalization. Okay, so the guideline is here. Firstly, you should check whether it is a generalization. Because generalization is very much different from the other two. So firstly, we will check whether the relationship type is a generalization. Okay, whether the relationship type is to show a classification, to show type and subtype kind of situation. If it is, then we will define it as generalization. So you will check the generalization first, whether it has the property of generalization. If it has, then we can conclude it as generalization. If it does not have, then we will proceed to check whether it is an aggregation. Okay. If it's an aggregation, you will have all these properties. That means whether it is part and assembly kind of interaction. Okay. If it is, then we will conclude it as aggregation. Okay. So if after the first check and the second check, okay, if you rule out the first check and also rule out the second check, then we will conclude it as associations. So this is the sequence to determine whether a relationship type is a generalization or association or aggregations. Okay, the last two slides, I will give you an example. Okay, I will leave the example for you to go through. So over here, I only want to mention one point. You may have, when you draw a class diagram, you may have more than one relationship type, okay, among classes. You may have more than one relationship type, okay, between two classes. In this case, okay. So this, from this one, you can see that. From this example, you can see that in a class diagram, we may have two different relationship type, okay, between two classes. The first one in this case is an association. Okay. Program chair manage program committee. And the second relationship type is aggregation. Program chair is part of program committee. Okay. It's a member, it's also a member in program committee. So it's part of program committee. So we have two different relationship type between these two classes. Okay. So the point to highlight to you is that you may have multiple relationship types, okay, among two classes or three classes or four classes. Okay. So it does not mean that between two classes you can only have one relationship type. Okay, there's so much about class diagram techniques. So now we have finished Unit 3. Okay, for today I would like to proceed to the first few slides of Unit 4. Okay, so next week then we will continue from there to study use case techniques. Okay, Unit 4 is to introduce you behavioral modeling techniques. Okay. So what we have studied in Unit 3 class diagram techniques is to model, to specify structural properties. So that means it is for structural modeling. Structural property are those properties that will not be affected by time, will not be affected by orders. In any system, okay, in any requirement, beside the structural property, okay, you will also have property that will be influenced or be affected by time, by order. Okay, So we have to define such property also, and behavioral modeling techniques is for that purpose. So in this unit, we are going to study a number of behavioral modeling techniques. Okay, we will study use case techniques in detail. We will study use case techniques in detail, then we will also study state diagram, and I will briefly introduce you sequence diagram and activity diagram in this unit. All these techniques are from unified modeling language. And these techniques can be used for requirement specification analysis and design. Okay, that is why UML called Unified Modeling Language. Most of the techniques in UML can be used across various stages in software development, not only restricted to a particular stage. Okay, for today I will just say a few words on requirement specification, on requirement gathering, because the first techniques we are going to study, use case techniques, is for specifying requirements. So before I introduce you use case techniques next week, I would like to give you a very quick introduction on requirement gathering and requirement specification. First, requirement specification. One of the important tasks in developing a software is to specify requirement, to produce a requirement specification, or we can call it as a requirement model. Okay, here list down a number. Here we list down various types of techniques that can be used for requirement specifications. Okay, you can see from here, from very informal to very formal. It depends on the needs. It depends on the need. Okay. Very formal case like define a requirement using mathematical logic. That is very tedious and very time consuming. And the advantage of doing that is once you define everything precisely using mathematics, then you can verify subsequently after you have developed the system, you can verify the correctness of the system automatically. That is the advantage, but it is very time consuming and it's very difficult. Okay, so usually we will only do that for those systems which demand, which cannot tolerate with any error, okay, which demand high accuracy. So we seldom do that. Okay. And you can see from here, we may also use very informal techniques, things like using English to describe requirements. And we can also use a prototype to describe requirement. Okay, remember that when we discuss prototyping model in Unit 1, we say that, okay, in prototyping, the objective of prototyping is to clarify requirements from the user. So every time we develop a prototype, we let the user check and see whether the prototype suit their needs, okay, can achieve their needs. So we will iterate again and again until the prototype, okay, can achieve the need for the user. Okay, so by the end, after we have fine-tuned the prototype until the prototype can satisfy the user needs, that means that prototype system has implemented all the requirements from user. So in that way, the prototype can be served as a requirement specification also. Okay, so that is another type of requirement specification. Okay, the more commonly used type is this one, by using a correction that user scenario, by specifying requirement through specifying the interaction between user, external agent with the systems. Okay, so we are going to study use case technique. Use case technique belong to this type. Okay, this is the most commonly used techniques for defining requirement. Okay, that means outside-in approach by defining requirement, by defining the interactions that will occur when the user uses the systems. Okay, so there's what we are going to study. Use case techniques belong to the most commonly used type of requirement specifications. Okay, in this slide, I'd like to say a few words on gathering requirements. Usually, the software engineers gather the requirement, understand the requirement from the user through conducting meetings and discussions. So here are the guidelines. Okay. So during requirement gathering, okay, it will depends on the size of the project. Okay. If you are working on a very big project, okay, all your meeting, all your discussion may have to be very formalized. Okay. So everything have to be well documented, and when you conduct a meeting, you may have to need to do it in a very formal way also. Okay. You may need to appoint a facilitator so that if there's any dispute, the facilitator can moderate the situation if you are working on a very big project. Okay. For a small project, the meeting will be more informal. Okay. So these are some guidelines in terms of gathering requirement. Okay. I will just highlight the important point. The rest of the detail, I'll leave it to you to go through. Okay, the objective of requirement gathering is to identify the problem that your project will help to resolve, the system that you are going to develop will help to resolve. Okay. And to propose element of solution. Okay. So during requirement gathering, we should propose solution from business viewpoint, business solution, not how to implement it. Okay. From business, from the term that the user can understand. And when you propose solution, we must propose alternative. Okay. We cannot just straight away fall back to one solution. We have to look at the various alternatives and evaluate the alternative to see which one is more suitable. We should not straight away jump to one solutions. So these are the guidelines in terms of gathering requirement. And once the requirement is gathered, we have to prioritize the requirements. Okay. In terms of prioritization of requirement, okay, these are important points. You have to prioritize the requirement for implementation according to the importance and dependency also and resources. Depends on how many resources we have. Surely those more important ones we will want to implement as soon as possible. But that is not the only factor. Okay. You have to consider dependency also, because some requirement may need support from other requirements in terms of providing data or in terms of others needs. So if requirement A is very important, okay, but requirement A, when you implement requirement A, you will need requirement B to support it in terms of providing information. Then before you implement requirement A, you will have to implement requirement B first, because A needs the support from B. Okay, so you have to consider such dependency as well. Okay, so the end product, the deliverable that we produce from requirement gathering is a requirement specification, and we can call it as requirement models also. So the first techniques we are going to discuss is the basic object-oriented techniques for requirement specification. Okay, the name is called use case techniques. Okay, so next week we will study these techniques. Use case technique, that is the basic method for specifying requirement in object-oriented approach. Okay, so today I will stop here. Happy Chinese New Year. Okay. For those non-Chinese, yeah, happy holiday. Yeah. Enjoy your holiday.